Tel Aviv 360, Israel's largest and most diverse podcast.
Hey, you're listening to another podcast from the Physics and Astronomy School inside of the Department of Exact Sciences at Tel Aviv University. I'm Danny Tadmore. My first degree, I studied in the international program at Tel Aviv University. My guest today is Rafi Bistritzer, professor of physics at Tel Aviv University, also winner of the 2020 Wolf Prize. And today we're going to be talking about breakthroughs in ways to understand moiré materials, which are patterns that happen as a result of overlapping two-dimensional lattices. So if you could help us know where, maybe not in nature, but where in the world we see these patterns and what are their consequences?
So thanks, Danny, and nice to be here. So it's actually an interesting story how these moiré materials came to the world, because as you said, they don't appear in nature. And the way we began studying them is actually by a puzzle. So people saw that when you put two graphene layers, graphene is a two-dimensional material, one atom thick layer of carbon. When you place two these two graphene layers on top of one another and you twist them, they are electronically isolated. And this was a huge surprise. Mm-hmm. That's a big puzzle. Because each graphene layer is an excellent conductor, and the distance between the layers is very, very small. So it was very surprising to see that electrons that move through this material don't just hop between one layer and the other. So we actually began studying this puzzle, trying to understand why electrons stay localized in one layer and don't hop to the other layer. And what we found is that maybe contrary to what people expected, the twist angle has a very important role on the electronic properties of the material. And when you turn the twist to a small angle, the two layers are no longer decoupled, but they come strongly coupled. And this basically gave birth to this area of moiré materials, because once people understood that you have this control knob of changing the properties of materials, they came up with many ideas and many types of materials which you can build by this kind of twist. And this basically gave rise to this field of moiré materials.
Okay, so since it's an audio format, let me make sure I understand what we mean by these patterns. I'm imagining whenever you look at a mosquito net, and you look at it from just the right angle, if it's not very taut against its frame, and you see these overlaps. And inside of the overlap in the mosquito netting or similar materials, you start to see patterns that were not from the original thing. So is that what we're seeing in layers of graphene?
Exactly. So a moiré pattern is something very general. It's known from the textile industry way back. And it really always appears when you take one pattern and you overlay with another pattern and you either twist it or have different periodicities of the two patterns. And then what results is another periodic pattern, which is not mathematically periodic, but it looks to our eye as periodic, and this is the moiré pattern.
Could you elaborate what you mean when you say it's not mathematically periodic? Because when you look at it, it seems to the eye periodic. What is the difference, and why does that introduce difficulties? Why has that held the research back until recently?
Yeah, so a periodic structure is a structure where the periodicity exactly repeats itself, like a lattice. So you take one atom or you take some kind of a molecule and you place it at equally spaced distances from the origin. And you get something which is exactly periodic. When you take two periodic structures and overlay them with a twist, you get something that is not exactly periodic. If you look, although to the eye it looks periodic, if you look microscopically or zoom in on the areas that look periodic, the atoms there are arranged a bit differently. Now, it may seem like a small difference, but it actually, from point of view of theoretical physics, it's a big change. Because the entire field of solid-state physics is built, or one of its cornerstones is built on what is called the Bloch theorem. Bloch theorem is a mathematical framework to work with periodic structures. And, this is something that people have been studying for roughly a century. and we have a very solid understanding of how to understand solids, how to understand lattices, repeated structures. So when you make this small change and it's no longer periodic, it's not clear how to theoretically address this material.
So the Bloch theorem is the framework that we use to understand how electrons pass through very periodic materials like silicon, right? So we have very good understanding of how to do that. We're pretty good at silicon at this point. So the challenge up until now is figuring out how to transplant that knowledge that we have from semiconductors into other materials.
Yeah, so I would say that's the end of the story, but the beginning of the story was that it wasn't even clear if these materials had a good description. Because they're not periodic, it's not a priori clear that you can use Bloch theorem at all. But what we basically found is that although they're not exactly periodic, you can make, to an excellent approximation, you can treat them as periodic. And then, as you say, you can take this entire machinery of Bloch theorem and apply it to these materials and basically use all the results that were obtained in the last century for solids and apply them to these moiré materials. But find that these materials are actually very, very different than our typical materials.
But it must be rather difficult to research these things because what makes them special is their angle between layers. And I imagine it's really hard to shift two layers of graphene around compared to each other. You can't just get two layers and then start sliding them around. It's a very delicate thing. So how can we get around that? Right.
So when we started working on it, it was a kind of a theoretical concept. And actually, we did not have the technology to control the twist angle, as you said. And this took a couple of years, actually. So our initial work was in 2010, 2011 it was published. And it took roughly 7-8 years for people to really be able to control this twist angle. Finally, Pablo Guerrero from MIT was able to, in his lab, was able to do that. But it's completely not trivial. So that's I think that's one of the reasons why it wasn't studied in the beginning, because we simply didn't have control, so we couldn't really anticipate that the systems would be very, very different.
Yeah. Did he find a way to shift two different layers on top of each other, like change the angle of two layers that already exist, or just control the angle as you place them on?
So the way it's done today, usually you take one material, you break it actually with a tip. You just pick up half of the material and then you twist it. You can control the twist on the other layer. It's not perfect, but I think today we have much more control over this angle.
Mm-hmm. Could you go back again on what properties we see whenever we have these materials? What are we learning about?
Yeah, so actually it's a quite surprising phenomena, the things that happen, this moiré material phenomena. Because as I said before, let's consider the simplest system, let's say two graphene sheets, so two-dimensional systems that are placed on one on top of the other. And as I said, when you place them at a large twist angle, electrons cannot hop between the layers. Now, as you reduce the twist angle, the electron can better hop between the layers, and at small twist angle, it hops very frantically, really hops back and forth, very, very strongly. Now, you would think, probably, that, now the electron cannot just move within a layer, it can move between the layers, so it will be easier for him to move. But what turns out, actually, is the velocity of the electron is reduced. And this is a quantum effect, because the electron is not a particle, it's a wave. So when it goes back and forth, there is interference effects that cause the electron to actually be more localized. So we get this maybe kind of counterintuitive result that as the hopping between the layers increases, the electron becomes more localized. Its velocity is smaller.
I see.
And when this happens, actually fascinating things happen. And to understand why, one need to appreciate that in materials, there is always a competition between kinetic energy, the velocity of the electron, and the interactions between electrons. And usually, the kinetic term, the velocity wins. And interactions is a small effect. But if you make all the electrons kind of stop, almost, not entirely, but slow down very, very much, then what happens is that interactions dominate. And when this happens, all the most fascinating phenomena in physics take place. And this is exactly what happened in moiré graphene. What we see today is that when we reduce the angle and when interactions dominate, we measure virtually all the phases of matter that we know in one material by varying small parameters and all these interaction-induced materials that I was alluding to.
What did you mean by that? All the phases of matter in one material?
So for example, by changing the density of this bilayer graphene, twisted bilayer graphene, you can change it from an insulating phase, so a phase where electrons simply cannot move in the material. It does not conduct electricity, to being a superconductor. A superconductor is a material where electrons flow with no resistance. So just by changing the density by a bit, you turn the material from one phase to the other phase. So this is, I think, quite amazing, and this is very. This is one of the hallmarks. One of the great things about moiré materials is their tunability. So the ability to take a material and just by using a gate is basically kind of a capacitor that allows you to vary the electron density. So just by using this knob, you can turn a material from an insulator to a superconductor. That's, I think, a really amazing thing.
How do we get about studying the different patterns then, if it's difficult to get them to line? So when you say tunability, do you mean that the tuning is in the angle of it, or is it in the potential on top of the bilayer?
No, so the angle is actually, in moiré materials, the angle is fixed. Once you fabricate the device, the twist angle is fixed, but there are other parameters which you can vary, and because it's a two-dimensional material, you have much more control over the parameters of the system. For example, like I said, density. So you can basically very, very easily change the density within the system. So just to give you an example, for example, one of the kind of holy grails of solid state is high temperature superconductivity. Being able to drive a current through material at room temperature with no resistance. So when people study conventional high TC materials, before the moiré materials, each time they wanted a different density, they had to create a different sample by chemical doping. The way to change density in 3D superconductors, in high TC superconductors, is by chemically doping it. So you take one sample, you dope it in one way. You take another sample, you dope it another way, and you create this set of samples. Now you have one system which you just tune, a knob, change the density, and get a superconductor. And study its dependence on the density. So this really it's one example, but there are actually more knobs you can control.
I want to give context to the listeners on how much work this could possibly circumnavigate, and I want to go over what doping is, because I feel like it's a word that, unless you deal with semiconductors, it doesn't mean much outside of sports drugs.
Right.
So
yeah. So I'm saying, so doping is a way to introduce additional electrons in the materials by replacing one atom by a different atom. So you also change a little bit the properties of the material, but also once you do it, it's fixed per the sample. Yeah. So you basically, you chemically introduce electrons into the material. Right?
So this makes it so that we could learn things about these materials without having to continuously remake materials, which lets us iterate over different possibilities much quicker.
Exactly.
That's so cool. I want to move to the sound boards and how that helps us learn even more. I feel like this whole topic is basically is the creation of a window that lets us understand materials which are very valuable better. What is the difficulty that using the standing sound waves overcomes, and what does it let us study in this context?
Okay, so maybe I would just go one step back and tell you that moiré materials, or let's say twisted bilayer graphene, is certainly not the end of the story, just the beginning. So there have been done some major steps to move this moiré materials area forward, and I think there is still much to be done. So what people realized, one time they understood this twist angle has a potential that you don't have to stick to 2 layers. You can go to 3 layers, 4 layers, 5 layers. So it's not only a bilayer. You can be multi-layer system. So that's one thing, they took it forward and created a new set of systems which contain many layers. And by the way, we have today many two-dimensional materials. So it's not only that you have multi-layer, but it doesn't have to be graphene. It can be other 2D materials. So that's like 2 jumps that people made. One is going into multi-layer, and the other one is beyond graphene, using other 2D materials, such as, let's say, TMDs. That's one family of 2D materials that is often used. But I think the other thing, which I think I'm very excited about, it's actually some very new work that we recently did, is that you really can go even beyond moiré. So basically, you can ask yourself, can I create similar physics, similar property behavior without the need to take another system, overlay it and twist? Because, while we do have now a lot of control over this overlaying and twisting, it's not a trivial thing to do. And some materials you cannot do it with, they just break up. And also, once you do it, as you mentioned before, it's fixed. So once you have the twist angle it's not a dynamic degree of freedom. Once you create the device, it's fixed. So, we were thinking, how can we overcome these kind of limitations and create basically the same physical phenomena, but without these limitations. And the idea we had very recently is to create it using surface acoustic waves. So basically, what one can do is use piezoelectric materials. These are kind of special materials that know how to change voltages to mechanical waves and mechanical waves to voltages. So they can go either way. So basically what you can do is you can take a piezoelectric substrate and drive surface acoustic wave through this substrate and create a potential landscape. Now, this potential landscape is very similar in spirit to the moiré pattern. Why? Because the moiré pattern is basically, it's like I said, it's kind of a repetitive pattern that appears because the hopping between the 2 layers has the periodicity of the moiré pattern. Now, instead of this hopping, we have this surface acoustic wave driven potential.
I see. I want to go back and describe what potential is for people who are less familiar with electromagnetism. So tell me if this is an analogy that you agree with. The same way height and gravitational energy can be thought of as the inclination of something to fall. The higher something is, the more energy it has invested in the future of falling. The more electrical potential something has, the more, in a similar sense, energy it has invested in the movement of electrons.
Right. So I think that's a good analogy between potential energy of
like making a landscape of hills of electrical potential creates similar patterns, or you can make similar patterns to what the moiré materials create, and then it's a lot easier to study them because you don't need to get 2 very delicate things together that you can, and also now it's more tunable.
Right. So it's exactly that. Let me just emphasize that this analogy with potential energy of height is very good, but there is one very big difference, and that is that there is quantum mechanics coming into play. So the effect of this periodic potential is very fundamental to the electron. It's very influential on for the electronic properties of the material. So once you have this periodic potential, you create what is known as electronic bands. This electronic bands is basically, that's related to Bloch theorem, and that lies in the heart of all the microelectronic industry that we have today. And so controlling this height and this periodicity basically allows you to control the electronic properties in the materials in very non-trivial ways. Okay, so once we were able to play with the periodicity of the material and with the potential strengths, then we can basically control the electronic properties in really unprecedented ways.
I want to go back to what the bands are.
Yeah.
Again, analogies, let me know if you disagree with this analogy.
Okay.
We can think of a standing wave, like a guitar string, or any string where the front end and the back end are tied together. And if you imagine it vibrating continuously, there's maybe it's a countably infinite amount of ways that it could vibrate. But for our purposes, let's say it's finite, that since the end point and the starting point have to be fixed, there's only certain ways that it can vibrate. And the electron, being a particle wave, now we're thinking of it more as a wave, needs to have a fixed type of vibration. And the modes govern what kinds of vibrations or what kind of wave forms it could take. That's
a great analogy, I think. Let me just make the analogy maybe complete in saying that, in a guitar string, like you said, you fix the ends of the string. In an electron moving in a potential, what you fix is that once the electron moves over one periodicity, it basically sees the same environment. So you expect it to have the same, what's called in quantum mechanics, wave function, very, very similar wave function. So that's like fixing the ends of the string in a guitar is manifested in a electron moving in a periodic potential by the fact that you fix the electron wave function, that it has to be almost the same when it moves one period.
I see. So by now I need to step back. By controlling the potential around, by making arbitrary hills, in quotation hills, of potential on top of the material, you can then make arbitrary energy bands present.
Right.
Yes?
So you can, I won't say arbitrary, but you can have a lot of control over the energy bands. Yeah. You have much control and basically, till now we had what nature gave us, which is a lot, but it's very limited. But now we are entering this golden age of solid state physics where we can create materials with very specific properties. We understand kind of the basic blocks, not fully, but we do understand the basic blocks quite well. And now we are able to create new structures that have very different properties and design them for what we need, what we need is also, of course, technological advancement, but also to help us understand the parts that we still don't understand about the basic physics of solids.
I see. So I feel like now we've spoken about a window into a window that you can use the soundboard. Is soundboard the right term for what you would use the standing sound wave in order to make
surface acoustic.
Surface acoustic
soundboard
wave.
is a good name. Okay.
the surface acoustic wave in order to study the moiré materials, and you can use moiré materials to have a better understanding of. Help me there. That's where I'm.
Okay, so I'm saying basically this idea of using surface acoustic wave really goes around the need for a moiré pattern.
I see.
So basically we're saying we want to engineer something that looks like a moiré pattern, but without all the complications and limitations that come with overlaying two layers and creating this moiré pattern. So, but in the end of the day, we are creating something that is similar. It's a bit different in the periodicity. So let me again maybe emphasize the differences, and that will also maybe explain what's moiré pattern and what's why the surface acoustic waves maybe will take us to the next stage. But in a moiré pattern, once you overlay it in a certain angle, you basically determine two properties of the material. You determine the periodicity. It's a new periodicity. It's not the periodicity of the atomic periodicity, which is a few angstrom. It's a much larger periodicity of, let's say, 50 times larger. So you create kind of an atom, a lattice with a periodicity that does not appear in nature. So that's one thing, you control the periodicity. And the other thing is the interaction strength between the layer, the hopping strength between the layer. Both of them are controlled by the twist angle. You do not have independent control over each of them separately. You determine the periodicity and the hopping strength. If you could decouple it, then you will allow yourself to have access to much more possibilities. And this is what the surface acoustic waves do, because for surface acoustic waves, you have a separate control over the periodicity of the surface acoustic wave, which creates the potential, which is given by the frequency or the wavelength of the surface acoustic wave. But you also have a control over the strength of the surface acoustic wave. And these are two separate knobs. So now you are able to create these periodic structures, which are even larger than the moiré pattern. So basically they can range from maybe a few tens of nanometers to a few hundreds of nanometers. So that's way, way larger than, natural atoms. And what we started doing, and I think, this is really, really just the tip of the iceberg. It's just the beginning to see the properties of this kind of new family of lattices. Yeah.
Interesting. How did you get to the study of this in general? Like, how does this start?
Right. So it started, as I mentioned in the beginning, it started with a puzzle. And actually, I think it's an interesting story. It's actually Ellen McDonald, with whom I worked on this moiré puzzle, gave a question in the course that he gave, in condensed matter, how to describe hopping between two layers that are overlaid on top of another. And people came to me asking to help them get this bonus question. And I thought of it for a couple of hours. I couldn't figure it out. And eventually, a bit frustrated, I went to Ellen, I asked him, what's the answer? And he said, well, I don't know. So we started working on it. And this is really how it started, just by, just trying to understand a very curious puzzle. I think it's also nice that we started with understanding one phenomena, but we eventually got to understand the opposite phenomena. So we wanted to understand why the two layers are isolated, but eventually we understood that in different circumstances they can be actually very, very strongly coupled. So that's the way we started
and
this journey.
When you say they're coupled, for people who also deal with electronics and physics less, what does that mean? What does it mean for two things to be coupled like that? Right.
So for two layers that are overlaid, let's say with a big angle, they are decoupled. And what decoupled means is that if you inject an electron in one of the layers, it will stay in that layer. It simply will never hop to the other layer. So effectively, you have two systems which are isolated. One system does not know about the existence of the other. That would be considered isolated or decoupled. Once you reduce the twist angle, what happens is that the hopping between the two layers increases. So electron it will not stay in the layer it was injected in, but it can hop between the layers. And then the system, when the angle is large but still relatively small, the hopping will just be kind of a perturbative effect, meaning you still have two graphene sheets with a bit changed properties. But if you reduce the angle enough to 1 degree, what we call the magic angle, then you really have a new material.
I see.
So it's no longer a small change in each. It's not two graphene layers that are weakly coupled. It's a different system. It's it's magic angle bilayer graphene, which has a completely different properties than the single layers.
And is this the only angle speaking Tel Aviv 360? Did you look? I'm sure you've looked through all the angles. Are there other angles that have special properties? Or my intuition would be like, okay, what about 1 degree plus 180 or plus 90? Or what is do we see other things at other angles?
Right. So actually, it turns out that it's very sensitive to the angle, first of all. So if instead of 1.1 degree, you have 1.5 degree, things will disappear. So it's very sensitive to this twist angle. But there are other twist angles, very small ones. 1.1 is actually, for bilayer graphene, it's the largest magic angle. There is actually an infinite set of twist angles smaller than 1.1 in which you have this hybridization, but they're very hard to it's hard to observe them experimentally because it's very, very small twist angles. Probably, again, I can't say it with complete certainty, but it's probably the system is not completely stable. And there are other effects that come into play, and and therefore I think most of the work was done around this largest magic angle of 1.1 degrees. But in other systems, you have other magic angles. So if we take, let's say, what's called let's say a bilayer graphene, so that's a 2-layer lattice graphene, and put another bilayer graphene on top of it and twist them, you have another magic angle.
I see.
If you have for other systems, there are other magic angles that can be larger actually than 1.1 degrees, and
so 1.1 is specifically for 2 layers of graphene. Okay, I see.
Yeah. Right.
Interesting. So ideally, hopefully, this could be a way to find a new form of semiconductor. That right now we basically use MOSFETs and BJTs, but there could potentially be other, I don't want to say materials, other mechanisms for it. Is that the far down the road hope?
So I think our dreams are even bigger.
Oh, okay.
Because I think the problem with the current technology of MOSFETs and transistors is that you have today you have billions of transistors on a very small area, and you have to turn them on and off very, very at very high frequencies, and all these things creates heat. And this is one of the biggest limitations on today technology, how to get rid of this heat. And once you make it very, very small, this heating also basically destroys the transistor. So it's a very big limitation. It's a fundamental limitation. And, I think one of the dreams is basically to replace this entire technology with a superconductor, something that doesn't generate heat. So basically allows you to move electrons from one place to another, but without creating dissipation. So I think, that's maybe, one of the ultimate goals.
Wow. Do you have anything else that you want to get to? Like anything else that you really want to think that we can drive the ship together?
So I think, I think what's just to place kind of to give kind of a bird's view of the field of solid state. Mm-hmm. So I think we're in a very exciting times in solid state physics because we've spent many decades understanding the fundamental properties of matter, and I think we have good understanding. We don't have full understanding. For example, like this high TC superconductivity, but there are also other phenomena which we still do not understand. But we have some good understanding of the building blocks. But now we're entering a new era where we don't have only to understand. We don't have to only understand what nature gives us, but we can build new things. You can maybe think about it like transforming a pigeon to airplane.
Yeah.
So you understand why a bird flies, and you maybe understand the basic physics. But now we are able to create an airplane. We are able to create something entirely new, and it's not only. First of all, it can give us, of course, a lot of technological advances, but beyond that, it can open new physical regimes. It can make us ask questions that were not relevant for the structures that we had. That we have till now, that nature offers us. So that's why I really think, that these moiré materials, that's my hope, will do two main things. The first is, and this is actually something that is already happening, it will allow us to discover new physical phenomena. Because it gives us a wider family of materials. So we can observe different phenomena, we can observe the same phenomena in different systems and better understand the phenomena. So this is one of the promises of moiré materials is basically increasing scientific discovery, and this is already happening. Mm-hmm. And the other thing is basically creating some a huge technological leap, basically using the knowledge that we accumulate with these moiré systems and of course with other systems, and being able to construct materials that have properties which are not seen in nature. So I think these are maybe the two, looking ahead, I think these are the two routes that I see us going.
Awesome. Yeah, making things that the leap from only working with what we had in nature to being able to construct our own materials and refining it, it really gives a callback to the beginning of industrialization, where now we have refined metals, and the better we understand them, the better things can let the snowball build and grow larger.
Yeah, and I think this snowball analogy is very good because, if you would ask me, in 2010, whether these moiré materials, would make an impact, I wouldn't. I would never imagine, it will make such a large impact. And I think, the ingenuity of people that take these ideas and build on them and build new things, and this focus of so many people around this area, I think is almost certain to create this huge snowball that you talked about.
Yeah, it's exciting. Yeah. Awesome. Well, thank you very much for your time. For people who want to learn more about these materials and more about your work, where can they find you? Where can they
So actually, there is a lot of things on the web. There is my website, of course, but there is tons of materials on the web on moiré materials. Just type moiré materials at Google and you'll get there.
Awesome. Okay. Well, thank you very much for listening. Find us on Spotify, YouTube, all the platforms where you find podcasts. And thank you very much for your time.
Tel Aviv 360, Israel's largest and most diverse podcast.